Welcome to Chapter 2 on the basic concepts in machine learning. Here we build the shared vocabulary and the core ideas that the rest of the book will rely on. Every field has its own vocabulary, and machine learning is no exception. Think of this chapter as that vocabulary lesson, though it is much more than a simple glossary. By the end of this chapter, you should be able to distinguish supervised, unsupervised, semi-supervised, and reinforcement learning. Use terms like feature, label, sample, and dataset correctly. Tell classification, regression, and clustering apart, and explain the separate jobs of the training, validation, and test sets. You should also be able to describe overfitting and underfitting and the tension between them, separate parameters that are learned from hyperparameters that are chosen, and explain what generalization means and why it is the real goal. This figure shows the bias-variance trade-off. As a model grows more complex, bias falls while variance rises, and the sweet spot sits where their combined error is smallest. It is a picture we will return to throughout the chapter. Facing a new problem, the first question a practitioner asks is not which algorithm to use, but what kind of learning this is. That answer decides what data you must gather and rules out whole families of methods. Supervised learning works from labeled data, meaning every training example arrives with the correct answer already attached. It splits neatly into two tasks, which we will meet shortly. Unsupervised learning is what you do when nobody handed you the answers. A retailer might have a mountain of purchase histories, but no fixed idea of what its customer types actually are, and the goal is to let the data reveal them. Semi-supervised learning sits in between. Sometimes labels exist, but only a few of them, because producing each one is slow or expensive, so we make the most of a little labeled data alongside a lot of unlabeled data. Reinforcement learning has a different flavor entirely. It is the machinery behind programs that reach superhuman playing games, robots that teach themselves to walk, and systems that adjust prices or dispatch vehicles on the fly. Now to the basic building blocks. A dataset is simply a collection of examples gathered for analysis or training, and inside each sample live the features, the input variables the model gets to look at. Here is a small dataset for house price prediction. The first three columns are features the model can see, and price is the label we want it to predict. In this table, size, room count, and age are the features, while price is the label, the value we are ultimately trying to estimate. Let us make the distinction precise. A feature is an input variable the model uses to make a prediction, and a label is the target output it is trained to predict. Features are what you know. The label is what you want to know. Putting features and labels together gives the basic supervised learning loop. The model fits the relationship from labeled examples, then predicts on new inputs it has never seen. This figure traces the supervised learning flow. A model is fitted from features and labels. It makes predictions on new data, and those predictions are then compared with the truth to judge how well it has learned. Another useful way to sort problems is by the shape of the output you are after. That lens gives us three familiar families: classification, regression, and clustering. Classification predicts a category. Is this email spam or not? Is this transaction fraudulent or legitimate? Does this patient have the condition or not? Each one sorts an input into a discrete class. When the menu has exactly two options, it is binary classification. When it offers more than two, we call it multi-class classification. Regression is different. It predicts a number on a continuous scale rather than picking a category. Typical regression questions include how much this house will sell for, how many units a product will move next month, what tomorrow's temperature will be, and what the customer is worth over their lifetime. Whenever the target is a quantity that can slide smoothly between values, you are in regression territory rather than classification. Clustering groups similar samples together, but unlike classification, it works without any predefined labels to guide it. We might cluster customers by their shopping behavior, documents by their topic, or cities by their economic profile, letting natural groupings emerge from the data. Because there is no answer key, clustering is mostly a tool for exploration, segmentation, and discovery rather than prediction. Now, a model that only repeats what it has already seen is not impressive. A lookup table can do that. The real test is how it behaves on data it has never met, which is why we split our data carefully. The training set is the data the model actually learns from, the examples it studies to fit its internal relationships. The validation set is a coach, not an exam. We use it during development to tune choices and check progress without ever letting it stand in for the final test. The test set is the final exam, locked in a drawer until the very end. How much data goes where depends on how much you have, but two common recipes are 70, 15, 15, or 80, 10, 10 across training, validation, and test. Here is the key point. The test set is sacred. Touch it only once at the very end to report final performance. If you peak while developing the model, your reported numbers will be optimistic and your real-world results will disappoint. Two words beginners constantly mix up are parameter and hyperparameter, so let us pull them firmly apart. Parameters are the numbers the model learns from data during training, the values it adjusts on its own as it fits the examples. Hyperparameters, by contrast, are the knobs you set yourself before training even begins. Examples of hyperparameters include the value of k in k-nearest neighbors, the maximum depth of a decision tree, the number of trees in a random forest, and the learning rate in gradient descent. Choosing good hyperparameters is a craft in itself, and the validation set is the tool that guides those choices. For a model to improve, it needs a way to measure how wrong it currently is. For regression, a standard choice is mean squared error, the average of the squared gaps between predicted and actual values. Once you can score the error, training becomes a search for the parameters that make that loss as small as possible. Two failure modes haunt every machine learning project, and they sit at opposite ends of a single spectrum. Underfitting happens when the model is too simple to capture what is really going on, so it misses the pattern even in the data it was trained on. The sweet spot lies between these extremes, complex enough to capture the real signal, yet simple enough to ignore the noise. To state it precisely, a model overfits when it does well on training data but poorly on new data because it has memorized noise. It underfits when it does poorly even on training data because it is too simple. Good models avoid both. The trade-off is easier to trust once you actually see it in numbers. Imagine fitting polynomials of increasing degree to the same 11 noisy measurements. Training error keeps shrinking, but test error is lowest around degree 5 and then explodes as the degree 9 curve threads almost perfectly through the noise. This figure plots training and test error against polynomial degree on that small data set. Training error falls without limit, but test error bottoms out near degree 5 and then climbs steeply, the signature of overfitting. Pulling these threads together gives the idea the whole field orbits around: generalization, the ability of a model to perform well on new unseen data. It bears repeating because it is so easy to lose sight of. Good generalization rests on several things. Enough data that genuinely represents the problem, a model whose complexity suits the task, honest evaluation on held-out data, deliberate control of overfitting, thoughtful feature selection, and careful hyperparameter tuning. It is worth stating plainly, even a brilliant algorithm collapses on poor data. Common culprits include missing values, incorrect or inconsistent labels, duplicate records, biased or unrepresentative samples, and stale, outdated data. Two more data problems round out the list: irrelevant features that distract the model and measurement errors that quietly corrupt what it learns. To summarize, this chapter assembled the vocabulary and core ideas you will lean on for the rest of the book. We defined features, labels, samples, and datasets, and distinguished classification, regression, and clustering by the shape of their outputs. To turn these ideas into something you can run, let us train a simple classifier and watch the train test split work in practice. We will use the Palmer Penguins dataset, which records 4 body measurements: bill length, bill depth, flipper length, and body mass for 344 penguins of 3 species observed near Palmer Station, Antarctica. This code loads the penguins' data and drops rows with missing values, picks the 4 body measurements as features and the species as the target, splits the data 80-20 into training and test sets, trains a logistic regression model, and finally prints its accuracy on the unseen test set. Notice how a few of this chapter's concepts are quietly doing the work in those lines, from features and labels to the all-important train test split. Consider a case study. A video streaming service wants to know which subscribers are likely to cancel next month so it can reach out before they leave. In the industry, this is called churn prediction, and it is a textbook supervised classification problem. The service already records plenty about each subscriber. Because every historical record pairs these features with a known outcome, the setup is supervised, and because the output is a category, it is classification. The same caution from this chapter applies, and this small example contains the whole chapter in miniature. The following code uses the Penguins dataset as a proxy for subscriber data, training a gradient boosting classifier to predict churn and mirroring the streaming service scenario we just described. Here, the code loads the Penguins data as a stand-in for subscriber features, encodes the categorical columns into numbers, sets the species as the churn label proxy, splits the data into training and test sets, and then fits a gradient boosting classifier as the churn predictor. The classification report shows precision, recall, and F1 score for each class, illustrating how each subscriber segment or churn risk tier is predicted with different reliability. For further reading, James and colleagues' Introduction to Statistical Learning covers features, labels, the bias-variance trade-off, and classification accessibly, while Hasty, Tibshirani, and Friedman's Elements of Statistical Learning gives rigorous derivations of loss functions, optimization, and overfitting theory. Finally, the scikit-learn paper by Pedregosa and colleagues documents the toolkit used for all the code examples in this chapter. That brings us to the end of Chapter 2, our tour of the basic concepts in machine learning. With this vocabulary in hand, we are ready to start building real models in the chapters ahead.